All right, let's look at a couple example problems of exponential growth and linear decay. Here it says the growth rate for the demand for oil in a particular country is increasing at 7% per year. When you see that it's increasing at a percent per year, that's a huge red flag that you're talking about an exponential equation. It's different from a parabola, it's different from linear growth. When you're building at a percentage rate, it grows exponentially because every percent can build off a bigger base from the previous year, which is what causes the compound interest, which makes it curve upwards exponentially. Anyway, they ask for the equation, when will demand be double? Well, let's see what this would look like as a differential equation. If we saw this as a differential equation, I'll call this the demand for oil over dt. So that's a O for oil, not a 0. We would see that this would be the equation 0.07 dO of t, because it's an exponential model where the rate of change is equal to 7% times whatever the current amount is. Okay, so that's O for oil and O for oil. The rate of change is 7% times whatever the current oil is. Now we remember from the previous video that the solution to this equation would be as follows. It would be O, your oil equation of T, I'll call it OI for oil. Your oil equation for T would be equal to your starting amount times E to the 0.07 T. That would be, I'm sorry, I put a P there. That should be an O. So our oil equation is equal to our starting amount, which is what this 0 represents, times E to the 0.07 T. Now, that's your equation. It's your principal right here, your starting amount times E to however much time has passed in years is equal to your future amount. So let's go ahead and solve this equation. They want to know when the demand will be double that. So all I have to do is put a 2 here and a 1 here, and that would be enough to solve the equation. And in fact, you could have done 10 and 5 or 20 and 10. It really actually doesn't matter, as long as this amount is doubled your starting amount. So our starting amount we called 1 to keep it simple. This amount is 2, so because that's double. So we get 2 equals e to the 0.07 t, and then we can just solve that equation. I do that by taking the natural log of both sides, like we did before. And so that gives me the natural log of 2 is equal to 0.07 t, because the natural log cancels the e. So now you're just ready to use your calculator. Divide by 0.07, divide by 0.07, and when you round, you get an answer of about 9.9 years. So that's kind of interesting. If something is growing at a constant 7% rate, then its doubling time is only 9.9 years, which actually, if you think about it, is not very long for an entire amount to double. All right, let's now examine a second example. Here we've got a different growth rate. If the growth rate is 1.6%, then how long, if the growth rate is 1.6%, then how many years will it take to double? Same idea. All you need to do is just put 1.6 here and 1 here, e to the x. I'm sorry, I messed that up. If we want to know how long it takes to double, so we put 2 here and 1 here, e to the, we have 1.6%, so up here we put 0.016, add then a t. So 2 equals 1 times e to the 0.016 t. Your percentage rate goes here, and then we doubled, so we put 1 to 2. If you wanted to triple, it would be 1 to 3, just something like that. So 2 equals e to the 0.016 t, and then we do the natural log of 2 equals the natural log of e to the 0.016 t. Natural log cancels e, so we get the natural log of 2 is equal to, 0.016 t, and then you just divide by 0.016. And so if we do that, let's do that. Natural log of 2 divided by 0.016. And we get approximately 43 years if we round to the nearest year. So you see how a 1.6% rate that every year is every 43 years you will double, whereas if it's a 7% increase, then every 9.9 years you will double. Hopefully I did okay explaining these two. If you have any questions, please let me know. We'll do some more in the next video.